Okay, then I have the pleasure of welcoming you all to this course in classical mechanics. My name is Jakob Linder, and I work as an associate professor at the Department of Physics here. This course will be given in English, as will the majority of the material, which you will find on the homepage, and there are two reasons for this. One is to accommodate people who don't speak Norwegian, and the second is that the kind of physics that we will do in this course will introduce a lot of terminology, which you will also encounter later if you continue with more advanced theoretical physics courses. So I think it will be useful to you to sort of get acquainted with this kind of terminology. Just a couple of pieces of practical information to begin with. So the homepage of this course is found here, and then you click teaching or something like this to link. And the lectures are given on these days and times, but there's a small change compared to the time schedule which you may have seen, which has been printed or sort of set by the administration. And that is that the guidance hour for the written exercise has been set to Tuesdays, but this has now been changed to Fridays. Fridays from 11 to 12, and the room is this one. Yes?
Is it possible to change that again?
Possibly. Is it a bad time for most of you, or?
At least those on technical physics.
Okay.
We have solid state physics.
So how many of you is this a bad time for? I see. Any other time on Fridays which would be better?
We have on solid states from 9 to 12 and optics from 12 to 2.
Okay, how about 2 to 3? Do you have anything there? Could work? Okay. So I'll post this on the webpage. 2 to 3, same room. Yeah. So I guess that's about it. And concerning other information about the course, like what kind of material we will use, there's a compendium on the homepage, for instance, and also recommended textbook, which is good to use. All right. Concerning the actual content of this course, I would say that classical mechanics is a very important stepstone in order to proceed to more advanced theoretical physics courses, if you intend to do so. What we will cover in this course is mainly that we will take the Newtonian physics, which I assume that most of you are familiar with from previous studies, and sort of place it in a more broad context, in a more general perspective. And in fact, this can be used not only to study mechanical problems, but also problems within electromagnetism, for instance. So a bit more specifically, most of this course, or a very big part of this course, is going to revolve around the introduction of two specific formalisms. And they're known as the Lagrangian and the Hamiltonian formalism. And these formalisms provide you with a tool to, in a systematic way, attack rather complicated problems within mechanics, consisting of not only one, but for instance, several particles. So they provide sort of a general prescription on how to approach such problems. And in relation to these formalisms, there are two very central concepts which are also of great importance in this course. namely symmetries and conservation laws. So this is the main ingredients of classical mechanics. Of course, there's a lot of other stuff that we're also going to have a look at, for instance, the theory of special relativity. But this is sort of the bread and butter of the course. Okay, so I was thinking that we could just have a little soft or easy start and just repeat some of the fundamental concepts which we will make heavy use of as we proceed. Is this writing big enough for those of you in the back? Yeah. This is Newton's second law. And already from this equation we can observe an important conservation law. Namely, if the force acting on a particle or some system is zero, it means that the momentum has to be conserved, or time independent, which follows from this equation. Now, we can imagine that we have some kind of system where rotation is important. And in such a case, it's useful to introduce what is known as the angular momentum. And moreover, something called the torque. And I might change between using n and tau for this torque, just so you know. Now, the definition of this angular momentum and the torque are given like this. And so we can observe that the torque is in fact the time derivative of the angular momentum. And you see this because when you act with a derivation operator on r and p, you get, for instance, r cross the time derivative of p, which is force. So this is the torque. But you also get the time derivative of r crossed with p. So the time derivative of r is just the velocity, and this is parallel with momentum. And so velocity cross momentum has to be zero. So again, we can observe a similar conservation law in this case, namely that if the torque acting on a particle or a system is zero, then the angular momentum has to be conserved. In analogy with Newton's second law over there. And let's also briefly remind ourselves of some of the properties related to how you can define work, the work sort of done in a system. So imagine we have some particle, for simplicity, which originally is situated in point 1 here, and it's taken to point 2 by some force. Then the work performed by this force, taking the particle from 1 to 2, is defined like this. It's the line integral of the force dotted with the displacement along this curve. So this is ds, for instance. In the special case where this particle has a constant mass, we can obtain a more explicit expression for the work. So we have that the following holds from the definition of the force. So this is acceleration, and this is ds. We can rewrite this as follows. Excuse me. And the final result is given like this. So we see that the work performed taking the particle from 1 to 2 is simply the difference in kinetic energy. Can you see if I write here? Is it too low? It's okay. So I use here T as a symbol for kinetic energy. So it's T2 minus T1. Okay, so that's one way of calculating the work performed in the particle. It's by comparing the kinetic energy after and before. There's another very special scenario, which is known as a conservative system. And the essence of a conservative system is that the work performed by taking a particle from point 1 to 2 is independent on the manner in which you do it. So it's independent on the actual path you take. The only thing that matters is the actual start and end point. And to express this mathematically, we can write the following. So this symbol, which I assume that you're familiar with, means that it's a closed integration loop. So we integrate for a closed contour. And this follows because if the work done between 2 points is independent on the path, then if you start at point 1, take some loop and go back to point 1, then the work performed should be 0, because the starting and end point is the same. So if we consider systems with friction, would you say that those are conservative systems? Why not?
Because you use force to move. You need energy.
Right, so you lose some kind of energy along the way. due to friction or heating or similar. So this excludes friction. Okay, so for a conservative system, the force can be written this way. And then it follows that the force mathematically can be written as the gradient of some potential. Because if the force can be written like this, then this property is automatically satisfied. And one point to note here is that the force remains the same even if you add some constant to the potential, V0. So it means that you can also redefine the sort of reference level of the potential energy and still have the same force. It doesn't change the physics. So just to be clear about that, the reason for this is that if you act with a gradient operator on a constant, you get 0. Okay, so if we now use this form for the force, we simply get that the work performed between point 1 and 2 is again given by the difference by the potential energy. Potential energy first minus the potential energy after. But now we previously derived that this should also be equal to the difference in kinetic energy. And so we can rearrange this equation and obtain the following result, namely that the sum of the potential and the kinetic energy before, in point 1, is equal to the sum of the potential and the kinetic energy after. So if we define the energy as the sum of the kinetic and the potential energy, we see that energy is conserved in a conservative system, which makes sense. Okay, so this was for a simplified case of just one particle. So what happens if you introduce additional particles to the system? Systems with multiple particles. So a natural starting point in this context is to try to write down Newton's second law for this case. So if you consider particle I and the time derivative of the momentum, so this dot above the p means time derivative. Then we know that one contribution to this should at least be the external force acting on this particle, if there's any external force acting on particle I. But in addition, since we have a system now with multiple particles, we should take into account the possible interaction between these particles. Or put differently, the possibility that these particles may influence each other. And we can take this into account by adding a second term here, which is the sum over j of Fji. And this Fji means the force exerted from particle j on particle I. So this is sort of a generalized Newton's second law for a system with multiple particles. So this is an external force, and this is an internal force. So assume now that Newton's third law holds. I just abbreviate this with N3, Newton's third law. Could anyone tell me what Newton's third law is? This should be a piece of cake for you. Newton's third law, come on. Yep.
Total linear momentum is conserved?
Yeah, I wouldn't formulate it quite like that.
The force exerted in one particle is equal to the force
Yeah.
exerted in another.
Exactly, yeah. So as you say, so the forces exerted by a pair of particles on each other have to be equal in magnitude but opposite in direction. So you can say that this is a law of reaction versus, or a law of action versus reaction. If I push this desk, there's implicitly a force acting back on the hand by the desk. So let me just symbolically write this. Like this. Okay, so how should we proceed now in order to obtain some information from this equation? Well, let's start by summing over all particles I. And the motivation for this is that if you have some macroscopic system with a macroscopic number of particles, it's going to be impossible to analytically try to solve sort of the equations of motion or solve this generalized form for Newton's second law for each particle. That would be madness. So instead, let's try to see if we can find some way to find a collective description of how the system acts as a whole, if this is possible. So we're summing now over all particles I. And like this. So assume here that there's no force acting on the particle by itself. So we're excluding this I equals J contribution. So this is just the momentum, the time derivative of momentum written in a slightly different way. We're summing over I, summing over all i's here for the external force, and then similarly here. This we can define as the total external force. So it's the total force acting on all the particles in the system. Now this term is actually 0. And the reason for this is the assumption we made about this law of action and reaction. That F in this example, F21 is equal to minus F12. And so if we sum over all the pairs here, the sum becomes 0. Let's introduce a useful quantity. The center of mass coordinate. So this center of mass coordinate sort of gives a weighted estimate of where sort of the middle of the object is from a mass point of view. So you see here that you weight the coordinate to each particle with its mass. And then you divide on the total mass. So what you end up with should be sort of the position in the object where you have the most concentration of mass. If you have an object where the mass is homogeneously distributed, so the mass is uniform in terms of density, then the center of mass position is simply the middle of the object. But if you have an inhomogeneous object in terms of mass distribution, for instance, if this compendium was heavier on this side than this side, then the center of mass would be somewhere here. This is just the total sum, total mass of the system. So if we now insert this here, we get so we started out with a somewhat challenging prospect, namely Newton's second law for each particle in the system. But then we tried to find some way to describe the system as a whole. So we summed over all the particles, introduced the center of mass coordinates, and arrived at the following equation, which physically states the following. The center of mass of a system of particles will move as if the total mass of the system was gathered in one point, namely the center of mass coordinates, and was acted upon by this total external force. So at least this equation gives us a way to describe how the center of mass of the system will evolve with time, how it will move with time. As we saw in the beginning of this lecture, there's a conservation law related to Newton's second law. And that is that if the total external force acting on the system is 0, then the momentum has to be conserved. And the same applies here, but just worded slightly differently. Namely, if you have a system of particles, then the total momentum in that system is conserved if there's no external force acting on the system. Because if F is 0 here, then the total momentum of all the particles combined has to be conserved. So let's now try to extend this type of reasoning to the angular momentum and the torque, which is relevant for systems where we have some kind of rotational motion. So similarly to what we did for the linear force F, we can define the total angular momentum of the system as sum over the angular momentum for each particle I. This is the time derivative. And if we now insert Newton's second law generalized for a system with multiple particles into this equation, we get something else. So remember, we had an expression for pi dot. It was equal to the external force acting on particle I in addition to the interaction from the other particles, this sum over j for each fji. So we insert this here. And we get this. So we see it again, the time derivative of the total angular momentum in the system is comprised of a contribution here from external forces and internal forces, the interaction between the particles, fji. Okay, so let's see if we can simplify this a bit. Let's focus on this last term, because it turned out that in the case for the linear force F, we could actually discard this last term coming from the interaction between the particles. So perhaps something similar is possible here. Well, this is the term we have to deal with. And we made an assumption about Newton's third law holding, that the force exerted on particle j by particle I has to be minus the force exerted on particle I by particle j. So if I add this term, I'm allowed to do that just by interchanging the indices I and j here. So I can write this as follows. Just by exploiting the fact that Fij is minus Fji. So if I do this, I can rewrite this equation like this. So the first term here is just the external torque, the torque acting on the system from external forces. And then I introduce this relative vector R1, Ri minus Rj. And this 1/2, it comes from the fact that I can rewrite one term in this sum as 1/2 multiplied by this. So for instance, so I made use of this property. So the only thing I did here was to interchange the indices for the second term here. Since it's a sum, the final result is the same. Okay. So can we do something about this last term now? Any ideas? So let me try to visualize this a bit. Let's say we have particle I here, particle j. They're connected by this Rij vector. There's some force acting between these particles. So in this situation, what happens with the last term?
Zero because they are relative.
Yes. If we assume that this force acting between the particles acts along the vector that connects the particles, then this term has to be 0. So let me write that. If the internal force acting between particles I and j lies along the line that connects these two points, these two particles, all of these torque terms coming from internal forces vanish. And this is not a very rare situation. We can consider, for instance, the gravitational force, which we know acts radially. So the gravitational force, for instance, between me and you acts along the line connecting us. Same for the electromagnetic force. I mean the Coulomb interaction, for instance. So again, we can discard this term with this assumption. So the final result is that the total angular momentum acting on the system of multiple particles acts as if only the external torque was acting on the center of mass of the system. So again, we can neglect all the internal interactions in the system, and this simplifies the problem a whole lot. So just to emphasize this assumption we made about the direction of the forces, this result depends on that the internal forces in the system are central. And by central force, I mean something that acts along the line connecting. It only has a radial directional dependence. Now, it's useful to actually decompose this angular momentum, L, of the total system and see what it actually consists of. So assume that we have some coordinate system, which is sort of the reference frame we use to describe the system. The origo is here. And let's assume that the center of mass, the object is here, for instance. And the center of mass is here. So big R vector is the position vector to the center of mass. And let's consider particle I. Which has position vector Ri. So then we define So we see here from the definition that Ri prime is this vector. It's the difference between the position vector of particle I, difference between that and the position of the center of mass. Okay, we'll take a break, 15 minutes.